Hello, S3. We're going to move on now with our radiation work. I've put a title for you there. If I write on the whiteboard, then you should make sure you get a copy of everything that's written on the whiteboard. That should go into your red jotter for future reference. So here's a title: How dangerous is radiation? And is there a limit? So that's a title. And it's in sort of two parts, really. It's a couple of questions which we're going to try and answer over the coming lessons. Okay, so we already know that radiation, whether it's alpha, beta, gamma, X-rays, background radiation, we want to try and keep that to a minimum, because the more radiation you're exposed to, the more damage it can cause to living cells. So here we go. Okay, you might need to stop the video. You can press pause while you're writing and copying. Or if you can keep up with what I'm doing, you can write it down at the same rate that I'm writing down. If you have trouble with your handwriting, you may need to type it, or it might be possible to get some screenshots of the whiteboard as it appears. So when I get to the bottom of a screen, you might be able to take a screenshot and possibly get that printed out and pasted into your red jotter, as long as you have got these notes and you have them to read at some time in the future. Okay, so it's important. We need to try and measure all these different types of radiation over a period of time and then compare that to some sort of national limit. So I've said, is there a limit? Well, there is a limit. So it is okay. Now, you could go through the whole of your life and not be exposed to any of these sort of types of radiation, alpha, beta, and gamma. I've met pupils who've said, well, the only time they ever came across any of these was in the classroom, and we have got some radiation sources locked away in a metal safe in the storeroom, and these sources of radiation do produce alpha and beta and gamma. We don't have any X-ray sources in the school, but you would be exposed to X-rays if you went to the dentist. Most people would have some X-rays taken sometime in their life at the dentist's, or if you end up breaking your arm or something like that, you get an X-ray in hospital. So these are quite unlikely. This is more likely. In background, as we've mentioned before in previous lessons, background you're going to be exposed to all the time. And we've already talked about how Highland Council monitors background radiation in schools, for instance. And if it finds that the background radiation is higher, as it did in some schools, then they have to make sure that they get rid of the radiation so it comes down below this national limit. So there are limits that are set as to how much radiation you should normally get. Members of the public have quite a low limit that's set. If you work in a hospital, then you are allowed to have a slightly higher national limit. And if you work in power stations as well, you're allowed to have slightly higher limits. So there are different sorts of limits, and this is a bit like having speed limits. You have a speed limit in some places in towns of 20 miles an hour, and you should keep to the speed limit. Then it might go up to 30 miles an hour, and then it probably goes up to 60 or 70 miles an hour. And it's important that people should try and not break the speed limit for safety reasons. And it's exactly the same, that there are national limits for people in different occupations. By occupations, I mean people who work in hospitals, physics teachers even, because we work with these every single year when we would get these out and demonstrate them. So hospital workers, people in power stations, physics teachers, and just members of the public. And the members of the public really should only ever get background radiation plus the odd little bit of X-ray radiation. So different limits are set for different people. And when I mean different people, I mean different occupations, different jobs that people have. So an English teacher, for instance, although they're teachers, they should really only be exposed to background radiation and possibly some sort of X-rays. Physics teachers, although they're teachers, they have a different job or a different occupation. So I'm allowed to have a slightly higher, but nonetheless a safer, higher level. Same with people in hospitals, same with people in power stations. The levels are all designed to make sure that you're kept safe in just the same way as I said before, that it's safe for in some areas to only do 20 miles an hour as a national speed limit or 60 miles an hour in different places. It's still safe. It's just the environment that you work in, you're allowed to have different limits. Right, so that's a page. And as I've said before, if you can't write this down, then you should perhaps get some sort of help from somebody and get this screenshotted. Is that a word? Screenshotted? Get a screenshot taken, get it printed out, and get that put into your book. And that should be done. If you're able to do that at home, fine. If you can't, then you probably need to get back to me if you need extra help. We'll try and sort out some extra help through ASN, and they could help you with the technical problems of getting this into your books, because you do need these notes. Okay, so that's going to disappear now. So you should pause that if you're one of those people who hasn't got it yet. There are written notes, there are course notes, and course notes provided by Mr. Garrod that were printed out and given to you just before Christmas are another source of notes. And if you really can't get any of that printing, any of this stuff that I've got printed, then make sure you firmly read the course notes. My notes that I'm doing on here are different from the course notes. There's no point in me writing just the same stuff that's in the course notes. I like to do something different, and then you've got two sources of information. Right, so the the next bit of work we're going to do is how do we build up this idea of a national limit? Now, it's just not one thing that's set down and you have a limit. We've got to do a number of different steps to get to this limit, a number of different stages. But what we're going to have a look at is the damage to tissue, because it's really damage to tissue. There's not a problem if you have some radiation and it's just beaming out and it's being stopped by a wall. The wall's not going to complain. The wall's not going to be killed or injured by radiation. So this is really all about damage to living things, and especially different types of tissue. So tissue is anything. It's not a thing that comes out of a box that you blow your nose on. Tissue is any part of your body. So you have skin tissue, you have brain tissue, you have kidney tissue. So it's different types of body tissue. So damage to tissue depends on. Now it depends on three things. It depends firstly, and you won't know this yet because we're going to do this very shortly. It depends on something called absorbed dose. An absorbed dose, I can't even spell it myself, D-O-S-E. Absorbed dose is how much radiation does your tissue absorb? How much does it soak up? The more radiation dose it soaks up or absorbs, the more dangerous it is. Different types of radiation are more dangerous than others. So it also depends on the type of radiation. And we've already done something about this. We know that alpha radiation, for instance, can be stopped by skin. So it's providing it's outside your body, it's not going to cause any danger to tissue, because skin tissue, the outermost layer of your skin, is in fact dead already. And it's only when you get down underneath the dead layers of skin that you get to live tissue. So alpha radiation gets stopped by dead tissue. So if I had a piece of radiation, let's just say I've got this bit of radiation here, it's a pen top actually, but if I take that piece of radiation and I put it in my hand, it's quite safe. I'm not going to be affected by it, but it cannot, because it cannot get through my dead skin. So it's not going to affect my living tissue. If I was to stick that in my mouth, or I was to swallow it, that would be another thing altogether. So alpha radiation inside the body is completely different. So the type of radiation is very important. And of course, lastly, what tissue or what body organs are being exposed. If you're exposing it to skin, not a problem. If you're exposing it to live tissue, then that is a problem. So we've got three things: how much do you absorb, the type of radiation, and lastly, the body organs or tissue that is exposed to the radiation. Now, I think some of these, the last two, we've done before. Certainly that one. This one I've just told you about, and we have covered that before. This other one here, absorbed dose, this is what we're going to move on to. We're going to have a look at what absorbed dose really means. So this is the first stage, something called absorbed dose. It's the first stage in establishing some sort of national limit above which you should not really be exposed to radiation. Just like the speed limit, you should not really go faster than the speed limit. Some people do, but they're more at risk. If you stay within the speed limit, then you don't have no risk at all, but the risk is less. So if you have a certain amount of national limit, providing you get less than that, you are at less risk than somebody who is exposed to more than the national limit. So just try and think about it like that. So the first thing we're going to do in a number of stages is we are going to find this thing called the absorbed dose. And we already know that it's got something to do with the radiation dose that is soaked up by different types of body tissue. And so we're going to look at that. So what does it mean? And to be precise, how much energy, because all these types of radiation carry energy with them, and it's the energy that damages your cells. The more the energy, the more damage caused to cells. It's like you getting hit by somebody if you're out playing in the playground. If somebody hits you with a low amount of energy, it's not going to hurt much. If somebody hits you with a high amount of energy, then that is going to hurt more. So how much energy and carried by the radiation is, and here's this word again, absorbed or soaked up, okay, so it's got something to do with energy that's absorbed. Okay, energy absorbed. So there is an official definition. This gives you an idea. It's all to do with how much your body is soaking up. That's called the absorbed dose. The official definition, which if you are asked this, what is meant by absorbed dose, what is that? It's the amount of energy So to be precise, if we're going to work it out, we're not just going to talk about any human body. We have to say how much human body, and we're going to do it as the amount of energy absorbed by each kilogram of body tissue. So there's the second page. Pause if you need to. So I'm going to rub this off again. So let's say we've got a fixed radiation dose, whatever that is, and it's a sort of blob, an amount of radiation. What's called a dose. Okay, and let's say that amount, that fixed amount of radiation dose, could be absorbed by a small child, or it could be absorbed by a much larger adult. Okay, and what difference does that make? Okay, so let's have a look at these, and we could have, say, a small child might have, well, a mass of 20 kilograms, for instance, and a larger adult might have a mass of 80 kilograms. So we're going to have a look, and we're going to do some sums, because physicists like doing sums to work out how much radiation do you actually soak up, depending on how big you are. Okay. So, in fact, if you've got this amount of fixed radiation dose, it's much more dangerous if all of that radiation is soaked up or absorbed by a small child, because then it becomes concentrated in the small body. Whereas this radiation dose, the same amount of radiation, if that's absorbed by a large adult, then the radiation has a chance of spreading itself out much more throughout the body. And if it's spread out more, then it's less dangerous. Okay, so that's just what I've said. Much more dangerous to have that radiation in a small body, concentrated into that small body, where it spreads out more in a large adult. And if it spreads out more, it's not so dangerous. Okay, so we're going to look at a formula, because physicists like having a formula. So this fixed radiation dose, we're going to work out this thing called absorbed dose, depends on the energy carried divided by the mass. And energy carried is measured in joules. Units called the joule, which we've come across before. Named after a person. Joule was, his parents were French, but he lived in Manchester. His parents had owned a brewery, and they were quite wealthy with their business. And Joule didn't have to work because his parents gave him loads of money, and he was very interested in science, and he made some amazing scientific discoveries about energy. So the unit of energy is named after Joule. Mass is measured in kilograms. Now, that doesn't necessarily mean that you have questions that have numbers in kilograms. They could be in grams, in which case you'd have to find that out, what that is in terms of kilograms. Same with joules. A joule is actually quite a large unit of energy, and we want to keep the amount of energy carried and that you absorb, we want to keep that small. So we might use some sort of smaller units like the millijoule or the microjoule, and we'll do some more stuff about that. Now, this absorbed dose, once we've got the idea of a sum that's got something to do with energy in joules divided by mass in kilograms, we end up with the absorbed dose, and that's measured in a new unit. It's called the Gray. And again, this is named after somebody. I don't know who the Gray person was. I ought to go and have a look. So it's measured in grays. And just like joule is somebody's name, it's got a small j. The name of the person, Gray, has got a small g. But when we abbreviate it, we use capital letters for the first letter. So the abbreviation for Gray is a capital G and a small y as its abbreviation. So we can actually get a formula out of this, because we're going to use some letters here. We're going to use the letter E for energy, and we're going to use M for mass, and we're going to use D for dose, and we're going to get a formula which says D is equal to E divided by M. So D stands for the absorbed dose, D for dose, energy E, and mass, and that will give you a triangle. And I know that some of you like using these triangles, and we're going to put D down here and E at the top and M at the bottom. I'm trying to encourage you to keep a list of these triangles and formulae in the back of your red jotter. And since I've now got to the bottom of another page, you might like to pause that and make sure that this formula goes in the back of your red jotter with a triangle. And I've been trying to encourage people to do that. You may have forgotten about doing that. I think the last formula we did was A equals N over T, and that should also have gone into the back of your jotter with a triangle which has got A and N and T in it, ant. And the triangles are a useful way to remember how to do these sort of sums. Okay, so that's the end of my next page. Pause if you need to. So we're now going to do some examples. I'm going to do some examples on the whiteboard, which you need to copy down. And then later on, you're actually going to do some examples yourself. Some of those you can do in your course notes, because there is space for examples in your course notes. Some of the examples we'll be looking at are in a problem booklet, and you should be answering those in your green jotter. This is all stuff that you know about already. Now, whenever we do some examples, we need to remember our TUP for now. And just to remind you, table, prefixes, formula, number, answer, units, and we've already got this. Okay, so we're going to look at this small child. Okay, and the mass of the small child, as I've already said, is 20 kilograms. So I'm starting to make up my table, and I'm going to say that this poor child is going to get zapped with some energy, and that energy we're going to say is 25 joules, and I want to work out what is the absorbed dose. So here's my table. That's the first thing I've took for now. Now, P, prefixes. None of this is in grams. None of this is in millijoules or microjoules, so I don't need to sort out any prefixes. That will come later. So the next thing we need to do is we need to copy down the formula. D is equal to E divided by M. And as soon as you get that written down, then that's worth a mark from the examiners and people marking your tests. That's worth 1 mark. You need to put in the right numbers. 25 divided by 20. So the formula, N for numbers. Get an answer. So you get your calculator out, or I'll do it for you to save you a bit of time. And that is 1.25. There's my answer. And then I want some units. And I know that the units of absorbed dose are in grays. So there you go. There's the first one done. So I'm going to compare that with the adult. And we know that the adult is much bigger. And the adult's mass is 80 kilograms. And I'm going to use the same amount of energy, and we'll see how much the dose is, the absorbed dose, when it's spread over a much bigger mass. So same amount of energy, 25 joules. And let's work out the dose. And we'll do exactly the same thing again. D is E divided by M, which is 25, this time divided by 80. and I put that in my calculator and I get 0.313 grays. So this goes back to what I was saying before, is the bigger person is less at risk if that radiation is absorbed by the whole of their body rather than a small person absorbed by the whole of their body. So the adult receives a much lower absorbed dose. Now, actually, you wouldn't want the person to receive that much radiation on their whole body. So if you went into hospital, for instance, to get some treatment for, say, a cancerous tumor inside you, what you would do, and here you are, you're lying down on the treatment bed, and let's say that you've got some sort of tumor, say in your stomach here. You don't want to zap the whole person with radiation. So what you would do is you get some blankets. Now, I don't mean ordinary blankets. These blankets actually have lead sheets put in them. They're really quite heavy. And what you would do is you would put these blankets over somebody to just leave a space for the radiation. So the radiation would come zapping out here, but it might be in all sorts of directions, but it's not going to get through the lead. So the whole body doesn't get treated by the radiation, because that's quite dangerous. And the radiation just goes inside the person to treat just the bit that needs the treatment. Okay, so although we know that the rate is lower, what we actually want to do is direct the radiation to the person. So that's important. This is called shielding. So what do we do? Cover the person with lead blankets or lead sheets. It's usually inside some sort of plastic, 2 layers of plastic with the lead inside, and the lead bends and the blanket bends. And the radiographers, the people who are dealing with the radiation, they actually wear these lead aprons. It's just like an apron you'd wear in home ec to cook with. They're quite heavy, but you wear a lead apron, you put it on in exactly the same way that you wear an apron if you're cooking. And then the important body organs of the radiographer are covered up with lead that can't get through. So cover the person with lead blankets to only allow the radiation to get to the area that needs treatment. So what we'll need to do is we'll say that there's like a space here. Space for the radiation. And this is the area for treatment. And hospitals tend to use 2 types of treatment for these tumors. One is called radiotherapy, which is radiation, and the other type of treatment is called chemotherapy, which is where you take tablets or a liquid, you drink it, and it's chemicals that work inside your body that attack and hopefully kill off the tumor. So radiotherapy and chemotherapy are 2 different types of treatment. Okay, so we've got another sheet done. Right, so these are very basic, simple formulae. I now want to go on to some formulae where actually the number of joules is quite big, so I want to get to do some questions where the number of joules is lower. And we've already said that you only want to really treat an organ, so perhaps an organ might weigh half a kilogram or 500 grams. So I want to move on to some more problems now, where we are going to make a table and we're going to look at prefixes. Prefixes coming up next. So what sort of prefixes might we have? We're probably going to look at smaller units. A joule is quite large, a gray is quite large, and a kilogram is quite large, and we want to look at smaller units. So we might be looking at something like, for energy, instead of a joule, we might look at a smaller unit called a millijoule. And a millijoule is abbreviated M, small m, capital J. Now, I've said this before in the past, that we need to remember, you need to remember how much smaller than a whole number these things are. And you have to remember what milli means, and milli means 1,000th. Okay, you've got to remember these things, otherwise you can't do the prefixes bit and you'll be stuck. So a millijoule is 1,000th of a joule. Is 1,000th. Pretend not to use fractions like 1,000th. What we would do is use scientific notation, and the scientific notation would be 1 times 10 to the negative 3. 1 times 10 to the negative 3 in scientific notation is exactly the same as the fraction of 1,000th. You can put fractions into your calculator, it's not a problem. You should know how to do that. So if you come across a question that's got milli, you could enter 1,000th, or you could enter it in scientific notation. Or indeed, you could do that in what I would call a normal number. I don't know if that's the right word to use, but it's 0.001 of a joule. And I suggest you try and remember this or this. Put a joule there, so you know it's 1,000th. 1 times 10 to the negative 3 joules. Even that's quite big. And so we might have things called microjoules. A micro is a sort of U with a tail on it. And that is 1 times 10 to the negative 6 of a joule, which is 0. Now that's got 2 zeros in front. We have to move the decimal place 1, 2, 3 to get back. So the decimal place needs to be shifted by 6 places. So we put 1, 2, 3, 4, 5, and then 6, and you can count 1, 2, 3, 4, 5, 6 moves of the decimal place to get that. Or it could be that you use a fraction, you put a fraction into your calculator, which is a millionth, or 6 zeros. Milli is 3, micro is 6. So you'll need to remember these sort of things. Now we can use the same idea with grays. We could have a milligray. And that would be M capital G Y. And that would be exactly the same. 1 times 10 to the negative 3 grays. I'm not going to write that number out again. I'm not going to write that number out again, but you get the same idea. You can have a micro gray, where you have your mu. That's what this is. It's a Greek letter, and it's pronounced mu. Micro gray, and that's 1 times 10 to the negative 6 grays. Okay, and again, same idea, like that and like that, but instead of joules, grays at the end. Milli, still 1,000th. Micro, still a millionth. And then lastly, we ought to know about grams. So we're ticking off all of these things in our formula. Excuse me. We've got the dose, we've got the energy, and we now need the mass. And we ought to look at things like, well, we know the standard amount of mass is a kilogram, but you might have the mass of, say it was a person's kidney that was being treated, and a kidney might have a mass of 200 grams, for instance. I've never weighed a kidney, so I don't know if that's right. But 200 grams might be the mass of a kidney, and that would need changing. And you know that there are 1,000 grams in a kilogram, so you'd have to do the conversion to get it into a kilogram. You'd have to do 200 divided by 1,000, because there are 1,000 grams in a kilogram. And you could enter that into your formula when you're working out the answer, when you're putting the numbers in. Okay, so what is 200 grams as a kilogram? It's 0.0. Now count the number of decimal places. How far do you need? We've got 3 on the bottom, we've got 2 on the top. So 200 grams is 0.2 kilograms. Almost made a mistake there myself. Okay, 50 grams, for instance, would be 50 divided by 1,000. You can do this on your calculator, or you can do it as a fraction, and that would be 0.05 of a kilogram. So you need to be able to change grams into kilograms. You need to be able to change million micro grays or joules into grays as a whole unit and joules as a whole unit. So smaller units. So you'll need to remember some of these things. What do these different prefixes mean? And that's another page done. So here come some examples. So we've got a body tumor, has a mass of 600 grams, and it's exposed to 30 millijoules of radiation energy. And we want to find out is what is the absorbed dose. So I'm going to make my table. So I don't know what the absorbed dose is. So I'm going to put a question mark. I'm going to put the amount of energy is 30 millijoules. And I'm going to have to remember that stuff that I did on the previous page. And what do I do? This is the prefixes. I'm getting rid of this thing here. And I want to change it into joules. So I would do 30, because that's how many I've got. And the simplest way to do this is 30 times 10 to the negative 3 joules. Or you could do that and put it in as 30 divided by 1,000 joules and put that into your calculator, because your calculator is quite good at accepting fractions if you know how to do the fractions. Okay, I'll just take that out a minute. And I've got my mass is 600 grams. And I either know that is 0.6 kilograms, or I could do 600 divided by 1,000 as a fraction. A number of ways to do it. But there are 1,000 grams in a kilogram, so I could do it as 600 times 10 to the negative 3 kilograms. So again, choose whichever way you're going to do it. 600 divided by 1,000 can go in your calculator. Or if you know that 600 grams is 0.6 of a kilogram, you can just put that straight down as well. Or you can do it like this in scientific notation. Whichever one you do, it doesn't matter because you'll always get the same answer. So I've done my table. Here's my table of my information. I've dealt with the prefixes. I've got rid of the milli, changed it into joules. I've got rid of the grams, changed it into kilograms. That's the prefixes. I now want the formula. D is E divided by M. And this sort of thing, you need to write this down, but it does need to go into your calculator as well. So I'm just going to write down this as my sum, 30 times 10 to the negative 3 divided by 600 times 10 to the negative 3 as well. That has to appear on the page somehow. You could do 30 divided by 1,000. It's a bit cumbersome, 30 divided by 1,000 divided by 600 divided by 1,000. You could write that down, but it's better if you can, if you're going to move ahead with physics, it's better if you can do this in scientific notation on your calculator, on your scientific calculator even. Okay, so you put those two numbers in and you should get an answer of 0.05 grays. That may be the answer that appears on your calculator. It may appear in scientific notation itself. So in which case it would be 5 times 10, and it would be 5 times 10 to the negative 2 grays. It depends how your calculator is set up. It doesn't really matter because both answers are correct. Whatever answer you get on your calculator, that's the answer you should write down. If you get that on your calculator, it's a waste of time and you might make a mistake, in which case you're not going to get any marks because it's your final answer that's marked. If you get that on your calculator, but you then decide to change it to that and you make a mistake, if that's your final answer, because it comes after that one, then you're going to be short of marks. However, if that appears on your calculator, and some calculators can be set up so that it always gives you an answer in scientific notation, write that down, and that's your final answer, and that will get marked. Or if that appears on your calculator, write that down, that's the one that gets marked. Okay, so another page done. So a second example coming up now. And I've got a tumor of mass 300 grams. And that's going to get zapped with an absorbed dose and what we're going to do is we're going to calculate the energy absorbed. Okay, so we're going to start off with our table. We're going to do M is 300 grams. We're going to do our dose is 900 micrograys, and I don't know what the energy is. I've got to work that out. And so there's my table. Prefixes are going to be dealt with. You should be getting used to doing this now. 0.3 of a kilogram. Now this probably is better done in scientific notation, so it's 900. And then micro, you need to remember, is multiplied by 10 to the power of -6 grays. So that's my prefixes taken care of. Again, you could do that as 300 divided by 1,000 and put that in your calculator. Doesn't matter. Now, I know mathematicians would like you to have scientific form written as like 9.0 times 10 to the negative something. You don't have to do that in physics. That's an extra little step you don't have to do. If you've got 900, then write down 900. And if you know what micro is, times 10 to the -6, write down times 10 to the -6. There's no point in trying to turn that into proper mathematical scientific notation, which would be 9.0 times whatever it is, 10 to the negative, I think it's 4. No point in doing that because you're just going to make another mistake, and you don't want to make mistakes. You want to keep the opportunities to make mistakes as small as you can. Now, we haven't used the triangle so far because I've just been using the same formula, but we do know that D is equal to E divided by M. And so from that, I can get that E is equal to D times M. This is one way of doing this, where you remember the triangle and you can write these things down like this. I'll show you another way in a minute. Some people like doing it a different way. So I'll do 900 times 10 to the -6 multiplied by 0.3. Now that is, I think, 2.7 times 10 to the -4, and don't forget your units at the end. Some people prefer to stick with the usual formula that you have, which is D equals E divided by M, and they like to put the numbers in first, and in which case you do 900 times 10 to the -6 equals E over 0.3, and you then have to do some rearranging. You'd have to take that 0.3, cross multiply it up there, multiply the 900 times 10 to the -6 by 0.3 to get E. It does not matter which one you do. You're going to get the same answer both ways, okay? So that would be an acceptable alternative. That may appear as 0.00027. And if that is the number that appears on your calculator, that is the number you write down as your answer. Do not go changing that to that or changing that to that. Write down whatever you see in your calculator window, and that's good enough. We're trying to minimize the number of places where you can make silly mistakes. There's only 3 things we need to do here. Is get the formula, because that gets a mark. Put in the numbers, that gets a mark. And get an answer together with its units, and that gets a mark. Any opportunity where you go and change this here or you change something else is an opportunity to lose marks, and we want to cut down on that. Okay, so that's my page there of worked examples. What you are now going to do is you're going to do some practice problems. I'm going to put these in into an assignment, but you're going to do some practice problems, and there are problems in your course notes that you got given just before Christmas, and I will put in the assignment which problems you need to do. Those problems in your course notes do not come with answers, so I will post up a separate post later on. It's not going to be immediately. I will post up a separate post that actually shows me working out the answers in the course notes, because there are no answers. In addition to practice problems in your course notes, I will be asking you to do some practice problems out of the problem booklet, which is on your Google Drive. They do have answers, but they don't have the working. They do have the final answer in the back of the booklet. So what you need to do is when you're doing these practice problems, and you should be doing those in your green jotter, when you're doing practice problems, you write them all out, you do the Tupfenau thing, and then you go away and have a look at the final answer that's in the back of the booklet, and you check your answer, your final answer, with the answer in the booklet. Now, if you've done it wrong, you must have made a mistake either with the formula or with the working, and then that would be your opportunity when you're self-marking. That's your opportunity to have a look and say, well, why did I get this wrong? And if you still can't work out why you've got it wrong, then you need to either ask a friend or you need to come back to me and say, look, I can't do question so-and-so on this page. I can't seem to get the right answer. Occasionally the answers in the back are wrong and it confuses people. So you will have some stuff to do in the assignment, which is course note problems, practice problems. You will need, as part of your assignment, to get all that written up or pictures pasted or whatever you're going to do. I will also give you a reference to BBC Bitesize, so that you can have a look at some stuff and you know where to find these things. And there's lots of information about radiation, National 5, on the BBC Bitesize. Make sure you go to the Scottish National 5 section. You don't go off to the English GCSE because it will have some different stuff. So I'll stop there and you can get on with finishing off your notes or moving on to the problems.